It's 35 past the hour. I guess we are ready to start the panel. Duncan is gonna moderate the panel, so go for it, Duncan.
Okay, thanks a lot. It's been a great set of talks. And the way I'd like to do this is, I'll kick it off with some questions, but I'd love to get the audience to also participate. But I'll say that my key objective is actually to see where the panelists agree and where they disagree. So, and because I think there's always a lot to learn by understanding where the disagreements are, because that signals kind of fertile areas for future research. So if audience members would like to offer questions, you can do that in the chat, or you can do that by raising your hand. But I just ask that you use questions that, at least a couple of panelists could respond to, rather than very detailed questions about one panelist's talk. So I'll kick it off with one question, and the pretext here is that I'd say I thought one of the really exciting things about today's talks was the way in which our speakers are making efforts to include knowledge about the physics of power systems into their learning applications, and sort of realizing that what I see is this real fertile ground of taking what we know about physics and what the capabilities are of things like RL and neural networks, to sort of blend those together to maximize the impact of the two. So challenge is that incorporating, though, I would say a challenge is that incorporating those physics it involves knowledge about the system. So in Zico and Bausen's case, we need the Lyapunov function. In Spiros's case, you need the swing equation. But one often sees that ML approaches, they shine in areas where you don't have much information, and we want to use these as black boxes. And maybe those are areas where we want to be pushing the frontier. So I guess the question, or the question is, does what we see here so far in these kinds of results imply limits to what we can do with AI and ML in power systems applications? What I mean by that specifically is, because we see that incorporating the physics is such an important part of making these methods work well, does that imply that there are boundaries, or that there is a frontier that we need to get across in terms of using these AI and ML approaches? Or are we always going to be sort of constrained by having a model of the system? And maybe I'll let Bausen kick it off, but I think a lot of the panelists will have things to say here.
Sure, thanks, Duncan. So, right, so whether black box or do we always need a model? I guess so, for our work, we tried a black box approach. It didn't work, right? So that's one reason we had a model. And a little bit deeper there is, I think if you look at a lot of sort of more traditional machine learning applications, you say this is the data, then everything is in the data. Right? In the entire world, your universe is in this data. You try to make some sense out of this data. But in our application, sometimes we have, we don't have that big of a data set, especially given the size of our systems. So we may, instead of big data, sometimes we run into this sort of small data problems. As we have data, but not everything is described by the data, or we can't get everything out of that data set. Then you need a model, right? Because to constrain for the space you're working on. So I think, you talk about if you have a lot of data, right? If you stream synchrophasor data from all the buses in the system, put them all together, do some learning there. Maybe a more black box approach could work there. But I think right now, given the data sets we have, some physics will be helpful. And Zico, I guess, Kevin, what you talked about, do you have thoughts on this?
Yeah, panelists, go ahead and jump in.
Yeah, absolutely. So I'm not quite sure I follow the question entirely in terms of like what does it say about the limits of the system, or
Not so much the system, but the limits of what we can do with AI and ML.
With AI methods. Yeah. So I mean, I don't know. I would sort of just because we need models to do it doesn't mean that we can't do it with AI, right? But I think there actually is an important point here, which I think also Maria alluded to, which is, you know, we're not comparing here to maybe the state of the art in nonlinear control either, and sort of we're kind of taking it almost as a given that like we want to be doing AI methods, we want to be using RL here, and we just can't do it yet. So what does it take to do it? And what we're demonstrating it on then ultimately are sort of simulated scenarios where we do know the true system, but where we are sort of either it's nonlinear, so we can't quite do exact optimal control, or something else, right? Just to be explicit about this, the real potential benefit of these methods is that they can apply to scenarios where we truly do not know the dynamics of the systems, or they're just too complicated to model, period. Right? Which there are a lot of problems like that, right? Especially when you have humans in the loop anywhere, and there's actual, you know, effects of people operating these things. They operate in statistically predictable, but sort of a priori very unpredictable manners. There are a lot of real scenarios where we just can't ever really know the system. And where we really want to apply machine learning to is in those scenarios. And all of this, to a certain extent, is kind of prelude to that, because we are applying ML and reinforcement learning to scenarios where, to these sort of test bed situations where we're trying to address their problems with this forward-looking view that what we really want to address is this bigger challenge where we don't know the real system, or where we just can't model it at all. And I think, but Tim, that's the real question, right? So what's going to happen if we do that? I think a precursor to being able to do that at all is to show essentially no worse than existing control, which is, and that's why we're sort of picking this up, is that, you know, existing techniques use these inaccurate models, they use this sort of these approximations, but ultimately once we get there, we have to turn it on and see what's the real benefit. And I think we're not there yet, and I think we want to be there. That's the promise. But until we actually get there and demonstrate it, I think that the answer to the question is going to be we don't really know what the ultimate benefit's going to be, because unlike in domains like Go or strategy playing games or whatever, we haven't actually demonstrated, you know, superior performance to the very best existing methods that we have for the current state of the art. And so this is going. For now, it's going to be aspirational to a certain extent, but I think, you know, the possibility exists very soon to get there.
I wonder if Ram or Spiros have a response to that, and maybe picking up on that idea that Zico mentioned about the unmodelable elements that we might ultimately incorporate into our control and optimization efforts.
You know, hearing the talks, you know, my talk was totally in a different direction, but I think there's an important point here that we often overlook, and which may be favorable to more of the type of approaches, which is, even though in desire we set up not to violate bounds, transmission limits, and voltage limits, and so on, in practice, of course, when you look at the real network, flows do cross the limits, because these limits are not, they're fuzzy, they're not hard constraints. And I think that, in a sense, why does that happen? I went and asked, you know, we did a project a few years ago where we were trying to learn the state of the network and the distribution network, and then tried to use machine learning also to see if we can replace their power flows simulator. And what they told us is, they don't even know how to model everything that's out there. Like, they buy some equipment from vendors, and these equipment has some control algorithm that's not exposed to you. And then what happens? So to an extent, I think the way, you know, so of course, stability is a big issue, but I would say on some of these things, I think we have to start thinking about what is the right formulation itself. That, you know, because in reality, we do all of these methods and we claim, okay, we did an OPF and we are not violating the voltage bounds. But in practice, in the network, there's a lot of violations. So maybe RL would have helped there and reduced the rate of violations. So we need those kind of test cases so people can design methods, I think, that could really you know, shine, because there is a lot of uncertainty. I think to what Zico said, it's not true. Even in the classical methods, their assumptions are not always observed in practice.
So, I mean, responding to all the points I think raised, if I want to structure a bit, so I think that there's no frontier for AI alone, right? If you have a big enough neural network, or let's say enough representation capability and enough data, you can actually represent any kind of function. So I don't think there's a barrier there. The barrier is how much data you have and how big of a network you're going to have. Because also, if you have infinite time, you're going to do that. I think that why the models come in are for two reasons. And I think, so also Bauzen said that we don't have enough data, and also we don't have enough, let's say, critical data, if you want. And I think somebody mentioned that, maybe Ram was in his presentation. So we cannot train a machine learning algorithm to actually do this control if we don't have enough unsafe data. And real data are very rarely fall in this kind of category. And that's why where models can help. This is number one. Number two is what I think we all have claimed is that models can help accelerate training. It's exactly when since you have all this knowledge about the model, why don't you use that? Or let's say, make sure that it's Lyapunov, I don't know, that it maintains stability, let's say, and make sure that your controller can apply that. And the final thing is also now what Ram said about these black box models. Indeed, I mean, any kind of component that comes from a vendor actually comes as a black box. But I mean, let's say it's an AVR or whatever, this is a governor, you know more or less how it works. You don't know the specifics, right? So why don't you include the model that you have? It can be a generic model in order to actually not need to have so much data to represent this function, and then get the actual data to regularize, or let's say improve the model and fit it into specific setup, right? So I see that more as a synergy rather than, yeah, helping accelerate training and better performance.
Thanks, Spiros. I'll give one round of before we move on to another question to see if any panelists want to disagree with anything that was said, or if it seems like everybody's kind of on the same page. But in the spirit of productive academic debate and trying to learn from each other, any thoughts, or should we go ahead and move on?
Maybe I can provoke a quick provocation for all the other speakers, since I saw your designs and it made me ask the following question. How much actual disturbance or noise in the measurements and kind of your assumptions can your optimal solutions tolerate? Meaning you designing this nonlinear thing, is it like really, it's like the equivalent of overfitting, right? Like it depends on having exactly the assumptions you took in, or is it robust to misspecifications?
So certainly I think that depends a lot on the specification, right? But the point of the robust control specifications is to be robust to misspecification, right? That sometimes is the point. Like you have some nominal system, and then you describe bounds around that system. You say, okay, I believe it's my system, and then I have some bounds around it. And under those assumptions, these work pretty well, especially if your system is linear, right? With bounds around it that capture both the uncertainty and the nonlinearities. That's sort of the ideal case, right? I think the bigger concern is that they're overly conservative. So when you start to demand these large bounds, these large uncertainty bounds, the system better be pretty stable nominally anyway, or effectively you'll find no control law that will actually stabilize the system, because you can have a system that is, you might need a positive gain or a negative gain depending on the set of uncertainty, and then all bets are off, right? You can't find one gain that will stabilize both of those. So they are either overly conservative and then they sort of have to rely on system being kind of a little bit too stable on its own, or they effectively will just not find a stabilizing control law. And that's the real concern. Now, to be clear, those things all apply to normal robust control, right? So in some sense, I am trying to sort of say, okay, if you like normal H infinity control, you'll love H infinity with RL attached to it. And that's sort of the motivating factor there. But I think there is a bigger point to be made here, that these things are just too conservative or the wrong objective to think about, period. And we really need to think about our specifications from first principles.
Okay, good. So I will continue to monitor the chat to see if folks have sort of like panel-wide questions, or you can raise your hand as well. And Maria has been chiming in a few times now, asking about ML and learning these models. So maybe Maria, you could just go ahead.
Yeah, so I think that this is real reality check. So I wanted to say something because I've been working quite a bit with industry, even through the startup. There is no good models. There is no data. You go even to the control center state estimator. He's very, very poor, uncertain data. And Ram said the same thing. So I'm just wondering if I see huge opportunities, almost like doing model identification the right way with machine learning tools. And so learn for a while what these models actually are at the level of granularity you need. Maybe for interfacing, you need one type of model. For designing very detailed inverter, you need different type of model. But can we use data that we have, knowing a little bit of the physics, to actually help the industry come up with the parameters of the model? That's a big, huge hole, right? And they're never even going to use our control because they don't have data. So can you guys comment on that a little bit?
Maybe I can a little bit reverse the question, become, let's say, and I don't know if it's provocative, but so because we talk about the models and estimate the parameters of the model, right? We want, so what Maria said is actually, maybe we can use machine learning to estimate the parameters of a model, right?
Yeah.
And I guess we're going to use this model in some kind of simulation in order to predict how our system will operate, right? So why should we estimate the parameters, and why don't we, let's say we have an A matrix, whatever, for a linear system, it's x dot equals AX, right? And this A matrix has a specific structure. So why should we maintain the structure? So why don't we let the neural network estimate the elements of that matrix in order to find the best fit, even if it does maintain the structure that we are used to, for example, for linear system. And it can still fit in the same simulation setup, right? So it might give us some, okay, we get a bit away from the physics in that case, but maybe we get I don't know, a more accurate performance of it.
Thank you. And just one more comment is we talked a lot about robust control, but in control, one excellent control approach to deal with uncertainty is sliding mode control. It is known that if you are in, controllable and things like that, you can actually be very, very insensitive to model uncertainties or to conditions uncertainties. That's what it does. And it was not used in power systems till power electronics came up. So now you have switching, and now, we can go big way with sliding mode control. So I would sort of use the benchmark for when we compare whatever we are proposing. Bausen, you are proposing new frequency control. I would compare it with the sliding mode control for the same conditions, because it is a huge opportunity to deploy at least something in power systems for fast dynamics that is robust with respect to uncertainties, and then learn further the details. So I'll stop here, Duncan.
Thanks, Maria. Okay, so I see that Stefano has a question for Ram, which is I think probably going to be specific to your talk. But Ram, I'll let you go ahead and answer this question, but then I have another sort of broader question for you to kick off discussion on. So the question here is about satellite analysis ready data. Perhaps you can just read it, or maybe Stefano can go ahead and just speak quickly.
It might be good for Stefano to clarify.
Yeah, Stefano, why don't you go ahead and go off mute and clarify your question?
Yes, you hear me?
Yes.
Hello? Yes. Okay, the question is, can we use analysis-ready data, let's say, from any source coming from satellite, and then ingest in AI tools where we can generate, let's say, modeling, for example, energy modeling, and all this process? The question is, instead of using, this kind of data, satellite data in a tube, like it was mentioned, and then generate it and use it for monitor the energy model, to go straight from analysis already established, ready, and then move directly to the AI model.
Yeah, so I think Stefano, in a way that, yes, so that is possible today. There is a few platforms out there like the Google Earth Engine that you can just, it's already ingesting all the satellite data, and it has all the facilities for you to just implement your machine learning. The challenge is always how you're gonna tune these weights. How many examples do you need, and what information you're trying to obtain? So what we thought was you need to be pretty clever about what combinations of methods to utilize to kind of generate reliable results without a lot of training data.
Yes, we are using the Open Data Cube concept developed by NASA in order to do all this process.
Okay, so picking up actually on this question, I think about data and what is available and what might be available in the future. I have a question that I think will provoke some discussion, perhaps across the panelists, but I'll start with Ram, because the question came up in the chat at one point about how much data should we expect to be coming from utilities or customers, aggregations, or in other words, here's how I would think about it. ML approaches can infer a lot of information that utilities might have internally already, or they could get with a bit of work. And the question is, do the kind of approaches, Ram, that you're exploring, do they push utilities to do more with their own data, or do they kind of push utilities into doing less because, well, we can just solve the problem with the sort of public data sets?
Yeah, I think this is actually relevant for all four speakers, as particularly if somebody tries to implement something with RL out there. But in my experience, Duncan, I started thinking, well, we don't have these open data sets, and what we can do. To my surprise, I receive a lot of emails from folks at utilities because of these papers. And the reason is they themselves want to be able to do some of these analyses and access some information that they don't have. And they have had lots of challenges in terms of what types of models you can build, particularly when you only have one piece of the data, you only have partial data. So for example, on EV charging, it's very common that they want to build charging profiles for all these, home chargers and this charger, because that's part of their planning. But they know, they only know partly where some chargers are, and they don't have data on the actual charging profiles outside of home charging, maybe some of the business charging. So there's kind of a disconnect there on their ability to build these models. So I think going forward, we will start seeing, at least commercially, some companies that are acting as intermediaries for DERs, collecting more and more of this data, and eventually, utilities will partner with them. That's what I see. But I think there should be, maybe from a system operator standpoint, if you want to integrate these resources into transmission, there has to be a more conscious effort about, okay, what are all pieces of information we need? We need some standards, and some of this information has to be published and accessible to do stability analysis and all the other things that might be required in the future. I think we haven't reached that scale yet. So, yeah. So,
Dawson?
Yeah. So to follow up on that, I think sometimes now they don't have data, as they don't have data in the way you want. Right? So we work with utilities here in the Seattle area, and a lot of data actually in sort of this handwritten logs that's built up over the last 60 years. Every event in the system is actually logged, and some engineer went take a look at it. But at the end of the day, you get a text file, and I don't know if that's sort of tens of thousands of pages long with people writing down what happened. And there is data there. I mean, that data tells us a lot about the state, the health of our system, how we should repair the system. If the next storm happens, what's the optimal way to schedule crew, things like that is all there. But they are not going to process that data, right, to make it nice for us to use. But I think a lot of need is, before some of the sort of more advanced method can be applied, to just make sense of those kind of data. Some NLP method or some way to get sort of large amount of data from utilities and translate to something that's more operational, be useful.
Spiros or Zico, I wonder if you have any thoughts just on how access to data might constrain or limit what folks working in your specific area can do. Is it access to data? Is it access to models? Like, what kind of transformation needs to happen there?
Yeah, I think that so before I worked with utilities, I had a notion very different from the reality about what they knew, how much data they had, and how good their data actually was. Right. I think as other people have mentioned, there's this notion that somehow like they have good models of the system and they understand it, but that's not actually true. They know enough to keep things running because if things are very over provisioned and things are set up in a way that makes them sort of inherently stable, but they don't really know. No one has very good models. So what this sort of means is that if your method requires a truly accurate model, not an approximation of the system, but a truly accurate model, there's no collaboration or NDA data sharing agreement that'll actually make your approach work. It's just not feasible. Like the actual cost would be far too much because you'd have to sort of generate the data to begin with almost anew. So I think in some sense, what this suggests to me is that in some sense, the sort of more bootstrapped approaches end up actually being the more viable ones in reality. So, Ram, the fact that you didn't get this information from utilities didn't actually stop you from being able to do it, right? Like this is fine. You're able to do it, and in some sense, being untethered from utility data is actually a big benefit because we have much more say and control over what we can do and release and how we can disseminate that information. Whereas when it's from utility, they have very, very tight restrictions on anything I've ever been able to share, even if it's things that I think have no real, don't have any obvious implications of security or otherwise. To me, they often don't want to share these things. And so I think that what this tells me actually is that we do need to consider what can be done just with data that we have available. And really almost not rely on utilities at all for the initial prototyping and development and every other aspect, and then bring them in when we already essentially have a product that can be enhanced by what they have. I think the other views are just also, you know, with different incentives, like different incentives of utilities versus you know, academic groups that want to, you know, we have very different incentives and different goals in this whole process. So I think I think there's going to be a lot of excitement, and when we do something cool, there's a lot of excitement from utilities, but it's just very, like, I haven't seen a wonderful example of, oh, as soon as they give us this data, we can do something amazing. It really typically is more a matter of, we have to build a system to begin with, and then if it is promising, we can further develop it in collaboration with the utility or with an ISO or anyone else like that.
So real quick, yeah, let me second that actually, because the barrier might not be the models or data, but actually convincing the utilities that there is value in specific things, or in seeing things in different way. And yeah, and I think now in terms of machine learning, there has been some move, at least I see utilities in Europe moving to this kind of maintenance or predictive maintenance. So they start making use of data in order to, and machine learning methods in order to predict when something will fail before failing. But for all the other applications we discuss, I think there is some way to go. As soon as they get convinced, or these barriers, let's say, get removed, then we're going to have access. Also, I mean, then yeah, data will come. Models maybe always be a black box, because that's what vendors give to the utilities as well.
So I think just to follow up on the thing, right? By data, it's often important to ask, what kind of data do we want, right? So you ask for model data, utility probably don't have it. But you ask for measurement data, for example, out of smart meters, they may have it. But as you said, the question is, convincing them that can be useful. I think, during a lot of my work when I was PhD as a sort of convex optimization, OPF, distribution grids and all that. But the most utilities said, okay, sure, it's convex or not. I don't have a Y matrix to give to you. I don't care whether it's convex, right? That's not a problem I can solve. But then nowadays, finally, that has made into a place where if you use machine learning, and if you just look at the smart meter measurement, PQ and V data, then that actually is useful to have a way to do voltage regulation. But I think, sometimes we ask them for model, they may not have it. But then we can convince them, if they can do measurements, which nowadays is very cheap to do and easy to do. Even with that, with some learning that can be beneficial to them, I think they're sort of more open to sharing that data.
I want to pick up on something that Spiros said about sort of success stories and a long way to go, and sort of blend this into another question that I had just about asking all of you about what you think is, what's the most exciting frontier, and maybe what, can you frame that frontier like in which part of the frontier is closest to being a success story? Where do you see the early successes happening outside of the predictive maintenance? And maybe, sort of think of answering the question as a way of kind of guiding folks that, might just be getting started in the area, or, younger folks that want to figure out what their next project should be. But Spiros, you can start, but, there can be any answer to this question, I think.
Yeah, probably there can. I think that, so seeing from what the utilities actually, what excites them. So reinforcement learning, if there is some way to actually being able to figure out a couple of things better than the current models, then I think that there are utilities that are interested in that. The other is, if we talk about how machine learning can get into the actual practice, it's more about accelerating computation speed, I think. So one is maybe develop a control that we were not able before, and then we can do it better. The other is accelerate computation speed, so I can now handle 1,000 scenarios in the same time I could handle one. If I trust what the machine learning algorithm will give me, as I trust my models at the moment, then I can actually assess millions of scenarios in a fraction of time, right? And this can help. So millions of inverters, a lot of uncertainty. We can get much better estimates.
Exciting to hear you answer the question that way, because that's actually right where some of my own work is right now. But I'll let others go ahead and kind of dig in on what you think the frontier is. Where's the early success story?
Sure. Yeah, sure. So I think for that and the planning is maybe from a practical perspective, maybe so the easiest place to use some of these techniques, right? I think Sparrow's talked about this. I think Zico also, how do you solve OPFs very fast? Now, if you use this in real time, so with the question, compared to existing solvers, how good are you? But if you look at some of the planning applications where the power flow model is just a copper sheet model, we don't even model any power flow because it's too computation intensive, right? We can't run it for, we cannot run that many scenarios. Whereas this machine learning models, because the baseline you're comparing against something that does not treat flow at all, then you can actually improve the quality by this sort of planning models by quite a bit. And that's relatively easier to implement. And so our utility is actually looking at this kind of techniques. Rather than say, if you tell an operator to say, okay, swap out where your control center, your ACOPF, you spend $10 million on, and use this neural network, that may not be, that may not be in the near future. But if you look at this lot of planning with renewables, or people look at EV charging, this kind of thing, where power flow becomes important. And you compare against a model that did not have power flow at all, there's a lot of potential. The kind of fast solvers.
Maybe I'm not quite getting the idea here, Bassem, but it seems like in the planning case, I would imagine that you're the challenge is that you don't have truth for supervising your models. Like you're talking about some future that hasn't happened yet. So what's the where do the models come in?
Right. So if you look at the Spanos, say the DCOPF work, right? So I can take a DCOPF. So if I plan a system, I can imagine this my future system is. I can train this using some simulation data. But often in planning, what you have to do is you have to run this through a million scenarios depending on the solar realization, let's say, right? Then normally, if you don't use learning and you still want to use DCFF, each scenario is a DCOPF, you have to feed it back to the parameters you have in the planning model. That just takes way too long for anything to happen. So if I had this, if I spend, let's say, a week training this DCOPF, then when I do planning, instead of running one DCOPF, then I can just plug them all into this neural network. And that reduces your time you solve one planning model, by orders of magnitude. Yeah.
Okay, great. Yeah, that makes sense. Ram or Zico, your thoughts?
Maybe I can quickly share some of my thoughts. In terms of what I find exciting for research, if you were to start today, I think this issue around climate adaptation is big. And one of the challenges there is that it challenges the standard formulations we have for problems. Because now the objective function has to think about impact in terms of people, right? And that's localized in space, and how to deal with that in kind of planning and so on. And there's some of the issues that Zico brought up before, which is like maybe there is not even a physics model to explain some of the things that are going on. So I think that area is super interesting, and I think there will be a lot of demand for that. In terms of early success, I tend to agree with Baussan. I think one area is certainly planning. I think right now, even beyond utilities, if you look at all the studies we try to do about deep electrification, there is a lack of robustness in the analysis because just we can't run the size of optimization problems that we need to run. But one thing that I think is very promising there is not just replacing teaching a neural net to solve a DCOPF, but maybe thinking about how some of the algorithms that were used in machine learning, you know, the gradient methods and all of that, how they can kind of go and solve, you know, these type of optimization problems. How can you take that kind of stuff and plug it into this new setup? Is it just out of the box, or do you have to do some different things there? I think that is very promising, because if you do that, suddenly you can use cloud computing to scale your solution instead of relying on what people do now. Like they have some dedicated kind of supercomputer to try to do the scenario planning for California. That's kind of the work Shmuel Oren does, for example. And the third, and another area I feel it's going to be very important and exciting is the whole coordination, like the DR coordination stuff. I think we did a lot of papers before, and then, you know, I spent like 5 years implementing something, and now what I'm seeing is there's a whole new, I mean, and there's a lot of practical issues there that we haven't captured properly. But now what I'm seeing is, well, there is certain resources that are already getting, you know, starting to get the scale to which you want to coordinate. And that's going to bring us a lot of problems and exciting problems in terms of more realistic approaches. And I bet like RL might have an application there. I think our community would benefit from like an, you know, open gym or something that people could go and have like some benchmark problems that we feel are industry relevant, that are suggested by industry, not by us. So that they say, oh, you know, these are things that are pretty close to things that we need. And, you know, if Zico has this amazing algorithm, or Bausen, okay, this already removes that initial hurdle of me proving to you the very basic that I'm not doing something stupid, right? And then you can, you know, there's still many steps, but at least you know what you're working for.
Yeah, that's sort of, you know, pivoting to Zico, if you want to say anything. I mean, it reminds me a little bit of the red data set that you started your career with. I don't know if you want to pick up on Ram's idea there.
Yeah, it's funny. It's still like my most, I think it finally got surpassed as a cited paper with my recent, more pure deep learning stuff. Finally surpassed it. Boy, I think there's a lot, I mean, there's a lot to unpack in that question, actually, because I don't think what's maybe most interesting necessarily does always correspond to what's going to have the shortest term impact, right? I think if you want to look at what's going to have impact, it's things that are in some sense in the critical path of current utility problems, right? And these aren't always the grand challenges of how do you optimize all the devices on the grid in a distributed fashion to decrease emissions and make the grid more sustainable. It's often things like how do you know which devices to maintain with predictive maintenance, or how do I catch, you know, people stealing energy and stuff like that, right? Which are really crucial problems in real operations, but they necessarily aren't necessarily the ones that academics would want to first dive into. So there is this divide, I think, between what sort of what problems are in some sense most the problems that are most academically relevant, like Ram mentioned climate adaptation, for example, and the problems that utilities need to solve right now, of which there are numerous ones that could have a substantial impact, but maybe aren't the sort of the super long-term vision ones. Methodologically, I would echo something that Ram mentioned and that Maria mentioned too, which is there should be a better appreciation of automatic differentiation within power systems. Automatic differentiation is deep learning, to put it sort of bluntly. Deep learning exists because of automatic, as it does right now, because of automatic differentiation, because we have toolkits that let you take derivatives to these really complex models without thinking about it, right? And we also, you know, from our work, you know, from a lot of the work we do in implicit modeling, you could do automatic differentiation of optimization problems, of fixed point iterations, of PDEs, of ODEs. You can compute derivatives efficiently of all these things. We don't have to waste our time writing out gradient equations anymore in machine learning papers, nor do we have to do it in any other field. But I think this pervasive element hasn't really found its way into across every field yet. And if you were just starting out, I would look to be, you know, the evangelist of automatic differentiation everywhere to learn everything in power systems is where what I would advocate for. I mean, I have students that are kind of trying to do this already, so maybe it's not maybe it's already too late to a certain extent. But I think this is the technique. This is the frankly underappreciated technique, and because it is so simple mathematically, it's been around since the 70s. It's not actually a new approach, but it is actually the availability of libraries like PyTorch, which are fundamentally just automatic differentiation libraries. This is what's actually changed deep learning. This is what caused the step function.
So can you build on that a little bit? So we saw in Spiros's talk, he's using AD to, you know, with the models to construct your first and second derivatives. Give us more kind of applications, like yeah, go ahead.
I mean, so anytime you have a process that you want to optimize, the notion of AD is that you can get first order derivatives of any function. So any module, any compute module you have, you can compute the derivative of any function. Any function you compute from those modules, you can compute the derivative of. This means that anytime you have a computational process, I can differentiate it to get the sensitivities of how I can adjust parameters in those modules to improve some objective. So it really is this notion. It's the notion of first order optimization, but it's taken to an extreme in terms of any computational module is something you can differentiate. Now you can use that in the case of physics informed neural networks to do things like define a vector field and then ensure this derivative satisfies a certain equation. But you can also use it to just optimize any process you can imagine, because the way you optimize processes in deep learning and otherwise and most other ways is via gradient descent, right? And so you can take any process, you know, in any control law, any process, I mean, any control law, any model, no matter how complex, no matter how sort of many layers or modules or sort of like physics you build into it, you can always differentiate the free parameters to match some objective or to match some sort of set of equations you want to satisfy. And that's an incredibly powerful paradigm that is not yet fully appreciated. Even in machine learning, to be clear, it's not fully appreciated.
Maria, go ahead.
Can I add something?
Yeah.
I think this probably would take a very long discussion for me to explain, but you know, we in power systems, we really don't have real distributed control implementations. And people have been working on distributed, not decentralized, but distributed. You get information about yourself, your measurements, and just the neighbors. There is a lot of theoretical work, but by subgroup of people, and we can look into that. They show that if you learn the rate of change of what's happening on the other side, at the neighbors, you actually have a lot of probable performance. How the distributed, not decentralized, now it's almost like plug and play. And we've been working on that. I had a PhD and just finished at MIT. And this is why I mention AD, because to implement such distributed control, you need very accurate computation and information exchange on that derivative. So it is not just about optimization. It is about going from completely centralized to distributed. So we can talk about that more, but that is actually where a lot of this distributed multi-layering is going through AD.
Yeah, but so you had made this point in some of the talks, and I didn't quite follow, because when you say we don't have accurate derivatives, AD fundamentally is not about like estimating derivatives. It's about, given an analytic function or a computational function, computing derivatives from that in an efficient manner where you don't have to do anything symbolically, you just do it essentially computationally also. So I didn't quite understand how estimating derivatives relates to AD in some sense. But maybe this is a session to have offline.
Let's do that offline because I'm very interested. But I think there is a statement there to be made because there is a big trade-off with very fast communication requirements where you have communication failed. You actually can replace these with just information exchange with derivatives about what the neighbors are doing. And the entire power shaping, energy shaping control that a lot of control people are pushing for nonlinear control is fundamentally based on that. Yeah, so I think somebody mentioned, I forgot who mentioned the Nordic system oscillations, the nadir. I think Bao-Zheng, you mentioned, I just was on the PhD committee a few days ago at KTH, and they are looking into these nitty-gritty details of power electronics control of HVDC, and they are recognizing, strictly from control point of view, it's not machine learning, that you have to have the information about not just power, but rate of change of power. That information becomes now golden, and if you can get it with machine learning, efficiently and sufficiently accurate, I don't need 15th order derivatives. I just need rate of change of instantaneous reactive power, for example, to stabilize voltages, all sorts of things. I just finished offering a course at MIT on rethinking principles of modeling. We can no longer just stay in the swing equation because it's not applicable to inverters and to things. So we have to get these more elegant models that you can pose in light of control language that we understand. So I think the AD, we have come to conclusion that having that tool to compute AD is not really just about optimization. It's about how can you implement effectively distributed control at the fast time scale in a provable way. So Zico, I will follow up with you on that. Okay, I'm very interested, but I think that that's a fairly low-hanging fruit because they have more and more of these, Bao-Zheng mentioned, these inverter-based control, things go unstable, and blackouts happen. So you cannot do optimization because something can go unstable. So how do we fix that thing? Also using machine learning. And so what you're doing, Bao-Zheng, I think is extremely important. The question is, do we have enough realistic model to capture those? And when you have this mix of HVDC and power electronics, I think it's not sufficient to just have the swing equation type model. And but AD to me, at least, is a big opportunity.
Okay. I'm sorry to jump in here, but I think we're going to wrap it up now. Several folks have to go, and I don't think we can have a long conversation about a new question right now. But I want to thank everybody for joining, especially our speakers / panelists. Really extraordinary set of talks. I learned a lot, and it's just really exciting to see how things are moving so fast and bringing these fields together. So I also want to just advertise next Friday and the following Friday, we will have another set of 4 speakers on each day. And we do hope you can join. If you found out about this one, you have the link for the whole workshop. Alejandro, Maria, do you want to say anything quickly before we close?
Oh, yes. It's wonderful, really nice session.
Yeah, thank the panelists and again, it was great. And everyone for attending. I think it was a very exciting day.